In this lesson, we will be introducing the concept of time dilation. In the second lesson, we will be using math to derive the equation for time dilation, and in the third lesson, we will be explaining the effects of time dilation on the natural world. For anyone worried about deriving time dilation, the math behind it is surprisingly simple. Anyone with an understanding of algebra and geometry will be able to understand how to derive time dilation. Time dilation is a phenomenon included in Albert Einstein's famous special theory of relativity. It is the phenomenon that a moving object, relative to an observer, will appear to experience time more slowly to the observer. To find out why this strange phenomenon occurs, we will need to use the special theory of relativity. This theory describes the behavior of space and time and describes the behavior of objects moving at different speeds relative to each other. In order to describe these behaviors, the theory makes two important assumptions. First, it assumes that the laws of physics do not change between different inertial frames of reference. And second, it assumes that the speed of light, represented by c, is the same for all observers, even if those observers are moving at different speeds and directions. This second assumption will be crucial to our understanding of time dilation, because it states that no matter the speed or direction of the observer, known as the velocity, relative to light, the speed of that light will always appear to be constant. This assumption claims that the observed speed of light cannot be added or subtracted from the observer's velocity. This is not how any normal object behaves. For example, if two cars are traveling towards each other at 30 miles an hour, the speed that the cars get close to each other, known as their relative speed, is the sum of the speeds of both cars. In this case, the relative speed of the cars is 30 plus 30, or 60 miles an hour. This means that while an outside observer that is fixed in place would observe the cars traveling at 30 miles an hour, each car would observe the other cars driving towards them at 60 miles an hour. Adding speeds and velocities like this is perfectly acceptable in most cases. However, light does not follow these rules. If a car travels towards a particle of light, called a photon, at 30 miles an hour, and the photon zooms towards the car at the speed of light c, one might expect that the car will observe the photon approaching at c plus 30 miles an hour. However, this does not happen since, according to the special theory of relativity, the speed of light is always c for all observers. In this case, the driver would not observe the photon approaching at c plus 30 miles an hour. He would just see the photon approaching at c. This is exactly the same speed that a non-moving observer will also observe. Since the speed of light is the same for all observers, we will use the special property of light in the next lesson to show that time appears to move more slowly for objects moving quickly relative to a non-moving observer. And we will derive a formula to find exactly how much time has slowed down.